What implications does the excellent high-temperature stability of O3NaCrO2 have for its integration into real-world applications where elevated operating temperatures are common, and how might this influence overall safety, efficiency, and longevity of sodium-ion batteries? How do these observations about thermal stability drive future research directions in optimizing electrode materials for diverse energy storage applications? And what complementary strategies can be employed to fully leverage the benefits of O3NaCrO2's unique thermal properties? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the low capacity of O3NaCrO2 limit its performance as an electrode material, and what underlying factors contribute to the shortfall in capacity? How does the material's tendency to absorb water from the air affect its overall electrochemical behavior and stability? What specific reactions occur when O3NaCrO2 comes into contact with ambient moisture, and how do these reactions lead to the formation of electrically insulating compounds such as NaOH and Na2CO3 on its surface? In what way does the development of these insulating layers interfere with efficient electron flow and sodium-ion transport within the electrode? How does the generation of NaOH and Na2CO3 facilitate the migration of sodium ions from the interior of the material to its surface, and what atomic or molecular mechanisms govern this process? How does this outward diffusion of sodium contribute to the formation of particles inside the electrode that ultimately lead to the deactivation of the whole material? How significant is the role of these surface reactions in compromising the cycling performance of the O3NaCrO2 cathode over time? What specific characteristics of the O3NaCrO2 structure make it particularly prone to water absorption and subsequent degradation compared to other electrode materials? How can carbon coating on the surface mitigate these detrimental effects, and what is the mechanism by which such a coating prevents moisture-induced reactions? What improvements in sodium-ion diffusion pathways and electrical conductivity are observed when a carbon coating is applied, and to what extent does this surface modification enhance the overall cycling performance? In what ways might additional approaches beyond carbon coating, such as altering synthesis methods, modifying the surface chemistry, or controlling the exposure environment, further improve the long-term stability and capacity retention of O3NaCrO2? How can researchers effectively balance the need to protect the material from moisture while maintaining or enhancing its intrinsic electrochemical properties? What experimental techniques can be employed to monitor the formation of NaOH and Na2CO3 on the electrode surface and to assess the effectiveness of various protective strategies like carbon coating? What?